All right, so this is our last section of material for test 2 today. 7.2, so Friday will be another Hawks Day. Okay, so come if you want help, if you're caught up, or if you don't feel like you need help. Okay, do what you want to on that. So that will make Monday test review day, and then next Wednesday will be test 2. Okay. And then test 2 is, have we already gone over this? Did we do this last time? Okay, so test 2 is chapter 4, chapter 6, and then these 2 sections from chapter 7. Okay. All right, so this section in 7.2, we're doing something you probably have not ever considered. We're talking about different techniques for counting. Okay. Might sound a little weird, you just think either you count something or you don't. Okay. It's not always super easy to come up with a count that we want. So the idea is that in order to figure out a probability, we need to know how many possibilities there are. Okay, we need to know how many things we have in our sample space. The way we've done them so far is we've just listed out the sample spaces and then just counted. That's okay sometimes if the numbers are not too big. But the idea is if we have a really large number of possibilities, then listing them all out is a bad strategy. Okay, it would take a really long time. So what we're focusing on in this section are ways that we can figure out how we can calculate how many outcomes we're going to have so that we can figure out probabilities. So we've got a couple different things we're going to talk about. Okay? The first one is the one we'll use the most. Okay? Got this thing called the fundamental counting principle, and it looks kind of complicated from the slide, but it's not that bad. Okay? But anytime you see something called the fundamental something, it means it's important. Right? So with this fundamental counting principle, what we're saying is if we're thinking about we have multiple experiments going on, so it makes it harder to count how many outcomes we have. So all we're doing though, okay, if you get down to the bottom of the slide, okay, is we take the number of outcomes for the first experiment, multiply it by the number of outcomes for the next experiment, times the number of outcomes for the next one, until we get them all listed out, and we just multiply all those together. We're just thinking our way through that. How many outcomes do I have here? How many do I have here? How many do I have here? And then we just multiply them all together. Okay? That works a lot of the time, especially for the problems we're going to have. Okay? This is going to be our most used idea in the homework assignment. Okay? Because once we start getting into ones that are a little trickier, they can be kind of confusing. Okay, so we're going to focus on the fundamental counting principle, but we will see some other ones. And you do have a couple other problems in the assignment that use some of these other techniques. But what I'm trying to say is if you're stuck on the homework, try using this fundamental counting principle first. Okay? See if there's any way you can use it. All right, so when we're doing this, okay, when we're figuring up how many potential outcomes we have for each one of our little probability experiments we're doing, we really have 2 situations, okay, that we're going to see in just a second. But our 2 situations we have to think about are when we count something, okay, when we count an object or count an outcome of a probability experiment, is it possible for us to get that one again? Okay. Are we putting it back, or are we replacing it? So we call it with replacement. Okay. Sometimes once you get an outcome, it's off the list, right? It can't happen again. If that's the case, then we say it's without replacement. So you can think about like drawing a card from a deck of cards. So with replacement, we would draw our card and see what we get our outcome, and then put our card back in the deck. So then the next time when we draw a card, we could get that same card again, right? It's been replaced. So we still have 52 cards we're drawing from. But without replacement would mean we draw a card, we see what it is, and then we don't put it back in the deck. Then the next time when we draw a card, we're drawing out of 51 cards, and so it's going down by 1. And then the next time we draw a card, we'd be drawing out of 50. Right? That's something we have to consider when we're trying to count. Okay. All right, so let's use our counting principle we just talked about, and then we're going to do it in both of these situations. We're going to do one with replacement, one without replacement, so you can see what the difference is here. Okay. So let's look at this example. Okay. In order to log into our new email account, we've got to create a password. Okay. Says the requirements are that the password needs to be 8 characters long, consisting of 5 lowercase letters, followed by 3 numbers. So making it a little easier on us than it is in real life most of the time. Okay. We've got to have 5 lowercase letters and then 3 numbers. Okay. And then we have to have the 5 letters first and then the 3 numbers. Okay. But this one says if we are allowed to use a character more than once, okay, so that's that idea of with replacement. Okay. How many different possibilities are there for passwords? Okay. All right, so we're just choosing each one of these characters, right? So we're going to pick our 5 letters and then pick our 3 numbers. So we can just keep up with how many possibilities we have for each one, and the fundamental counting principle says we can just multiply all those together. Okay? So if we go to choose our first letter, okay, first lowercase letter, how many choices do we have for a lowercase letter? How many do we have in the alphabet? 26. So when we pick our first letter, we have 26 choices. Okay? But then we could use that letter again, it says. Okay, we're in a with replacement situation. So when we go to pick our second letter, we still have 26 choices. Okay? And that's going to be the case for all of our letters since we're allowed to use a character more than once, right? So for our first 5 characters, we've got 26 choices each time we pick a lowercase letter. Okay? Our first 5 spots. Okay, for our next character, we need to pick a number. So since we're doing single digits, how many choices do we have for a number? How many digits do we have? We got 1 through 9 and 0, so we've got 10. Yeah. 10 choices there. We could use that same number again. So 10 choices on the next one. And then 10 choices on the last one. So there's our fundamental counting principle. Okay? Just count how many possibilities we have for each thing, multiply them all together. Okay, this is a really huge number. It asks us how many possibilities we can have. If you do it in your calculator, you're probably going to get scientific notation. Okay? So here it is multiplied out. Okay? So we have 26 times 26 times 26 times 26 times 10 times 10 times 10. We'll get 11,881,376,000 different passwords we could have. Okay. Really big number there. Okay. All right, questions so far? All right, let's look at the next one. The same idea, okay, we still need 5 lowercase letters and then 3 numbers, but this time we're not gonna allow replacement, so that means once we use a character, we can't use it again. Okay, so this one works out a little bit differently. Okay. When we go to pick our first lowercase letter, we still have 26 choices. But then when we go to pick our second lowercase letter, we can't repeat, and we can't use the same one we used on the first one. So how many choices do we have this time? 25. Then when we go to the next one, we've already used 2 letters, so we're down to 24 choices. For the third one, we're down to 23 choices. Or fourth one, sorry. And then for the fifth one, we're down to 22 choices. Okay. So each time we use one, that takes it off the list of possibilities. So we're counting down each time we choose a letter. For our numerical digits, we start with 10 choices again, but then once we pick that digit, we can't use it again, so the next one we have 9 choices, and then the last one we have 8 choices. So we multiply those together. You can probably tell it's going to be a smaller number, right? Because before all of these were 26s, right? Now their numbers are a little smaller, and before all of these were 10s, and now they're a little bit smaller. But it always amazes me how much smaller it is. Okay. So let's look, if we multiply all those out, here we get 5,683,392,000. Okay. Pretty remarkable there that simply by the fact that we said we are not allowing repeat characters, we basically cut the amount of possible passwords in half, almost. That's one thing you'll never see in the real world when you're trying to make a password. It won't ever tell you don't use repeat characters, okay? Because that cuts the amount of passwords down. All right. So anytime we have a situation, let's go back, when we're not doing replacement or we're not allowing repetition, we're going to have this kind of pattern where we start off with a number of choices and then it goes down by 1, goes down by 1, goes down by 1, goes down by 1 the next time. Okay? So that type of pattern where we're multiplying numbers that are starting at some number and then descending by 1 every time happens quite often. Okay? So we have some notation we use to make that easier to write down. The notation we use an exclamation point to represent that. You may or may not have seen it before. And we call that factorial. So we just write the number and then an exclamation point. So here, instead of a number, we've got n, so you would call that n factorial. If it was a 7, you would read it 7 factorial. But the idea is that we start with whatever number is with the exclamation point, and we're multiplying, starting with that number, times the next number smaller, times the next number smaller, times the next number smaller, all the way down until we get to 1. That's the idea of factorial. Anybody seen that before? A couple of people, not me. And we've got one little note down here that's important. It doesn't make a lot of sense. You just try to reason your way through it, but we define 0 factorial to be 1. That just makes other calculations work out well. There are a few arguments you can make for that being meaningful, but it's okay for us if we just know if we have 0 factorial, that's just 1. It's similar to saying if you raise a number to the 0th power, you get 1. So the next little thing we want to be able to do is we want to be able to simplify these factorial expressions. Okay. So if we have something given to us with a factorial, we want to just be able to figure out just what number that is. All right, so let's look at a few. We're going to go through several here. So this one says calculate the value of the factorial expressions. So let's start with A. On A it says 8 factorial, so that means 8 times 7 times 6 times 5 times 4, 3, 2 times 1. Okay. And we can just do that the long way in the calculator. Some calculators have a factorial button. Okay, not all of them. Exclamation point, usually, yeah. I think I've got one. I'm not even sure where it's at though. So it's not too bad as long as they're not too long, right, to do them the long way. So just 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. This one works out to 40,320. Is 8 factorial. Questions on that one? Okay. Let's look at B. I've got each one on its own slide. Okay, let's look at B. So B says 3 factorial over 0 factorial. Okay, so 3 factorial, that's 3 times 2 times 1. 0 factorial, we just have to remember our definition. What's 0 factorial? 1, yeah. 0 factorial is defined to be 1, so this thing is just 6. Six over 1, just 6. Now, C, we get a little interesting here. So if you've never seen this before, it's, as far as math goes, it's kind of neat. Okay, so let's look at this. So we've got 89 factorial over 87 factorial. Okay, those are two huge numbers. Okay, probably especially during the pandemic, you've probably heard, maybe earlier on, you've heard people talk about exponential growth, right? That means something's growing really fast. Okay, that comes back around to having a number in the exponent. Okay. Well, factorials get big, they grow even faster than exponentials, even faster than exponents. Okay. I don't remember exactly. I think it's something like, so if you have a checkerboard, right, at 64 squares, 8 by 8, if you put 1 factorial pennies on the first square, that's just 1 penny, right? 1 times 1. If you go to the second square, you put 2 factorial pennies on there, that's 2 times 1, so 2 pennies. If you go to the third square, you put 3 factorial pennies on there, that's 3 times 2 times 1, so that's 6 pennies. And so it starts off small, but by the time you get to the 64th square, the last square on the checkerboard, you would have a stack of pennies that went past the moon. Okay? That's how fast factorials grow. Okay? They get big really, really quickly. So, saying that to say, even if you have a calculator that has a factorial button on it, if you try to punch in 89 factorial, it's going to be really unhappy. Okay? Yeah, so number's so big, graphic calculator can't handle it. Okay. But we're smarter than calculators. You might not feel like it sometimes. Okay. But we're smarter than calculators, so we can figure this out. We can figure it out. So let's think about it. There's something nice that happens that helps us. Okay. So if we try to do 89 factorial over 87 factorial, what would happen there? So 89 factorial, I don't even really want to write that whole thing out, but how it would go, right? We would have 89 times 88 times 87 times 86 times 85, and then it would keep going on and on and on down to the end. Right? We would end up with times 2 times 1, and then we would be finished finally. Okay. Okay, let's look at what 87 factorial would be. We'd have 87 times 86 times 85, and on and on and on till we ended up on the other end with times 2 times 1. So something nice happens here. The numbers on top are all multiplied together, so it's like one term. The numbers on the bottom are all multiplied together, so that's like one term. What happens if you have a number over itself? Yeah, it turns into 1, or we say it cancels, right? It turns into a factor of 1. So, you see anything we got on top and on bottom? Yeah, a bunch of stuff, a bunch of stuff. Yeah, so what happens here is really nice. Okay? The 87s cancel, the 86s cancel, the 85s cancel, all the way down, right? We could keep canceling all the way down. We've got the 2s cancel, the 1s cancel. So all this thing boils down to, it simplifies down to 89 times 87. And we can do that. So 88, sorry. Just looked at the wrong one. 89 times 88, sorry. Thank you for pointing that out. So 7,832. All right, so anytime you have a factorial on top and on the bottom, look for some stuff to cancel, because that happens quite a bit. Right? Good question. Yeah. But it's up to you. Yeah, it's up to you. Yeah, I mean, you want to get one answer, you could if you wanted to. That's less you have to type in your calculator. Right? 8 factorial over 7 factorial would just be 8. Right, because the 7 and everything down would cancel out. So it saves you a lot of punching on the calculator. You see that. Yeah. Okay. All right, let's look at D. D, it looks a little bit different. We're gonna use kind of the same idea. A D, we've got 7 factorial over 5 minus 1 factorial. So really we've got a couple of steps to do to simplify here. First, we're gonna do the stuff in the parentheses. So this would be 7 factorial over 5 minus 1 is 4 factorial. And then we can do some canceling. Because on the bottom we'll have 4 times 3 times 2 times 1. So everything 4 or smaller cancels. So we just end up with 7 times 6 times 5. I think that's 210. Okay. If you have parentheses, just do that part first. And then one more. We got an E here. And the reason why these last couple are weird, you'll see in a second, is setting you up to do a formula. So E here, we got 5 factorial over 3 factorial times 4 minus 2 factorial. So when we do our subtraction, that's 5 factorial over 3 factorial times 2 factorial. So if we write that one out, and then 3 factorial, 3 times 2 times 1 times 2 factorial, which is 2 times 1. So if you have multiple factorial expressions in the bottom, just cancel out as much as you can. So what I'm seeing is that 3, the 2, and the 1 will cancel. So this thing is 20 over 2, or 10. Okay. Questions on those? All right. So that's setting us up for another kind of counting, or two really, other counting techniques. Okay. You do have a couple of these in the assignment, but not as many as just that fundamental counting principle. Okay. Okay, so the first thing we want to be able to calculate is something called combinations. Okay. So the idea of combinations is we have a group of objects, and we know how many we have. So maybe we have a group of 20 objects, and we want to know how many different ways we could pick 5 objects out of that group of 20. The thing that makes combinations, specifically combinations, is that we don't care about which order we pick the objects. Okay. So like if we got different marbles, okay, it doesn't really matter which one you pick first and which one you pick fifth if you're choosing 5. Right? The order does not matter there. Okay. That gives us a combination. We'll see formula in just a second. Okay. If the order does matter though, okay, so the order in which we choose the objects matters, then instead we use something called permutations. Okay. So same idea, we're picking some number of objects from some group of objects, but the order matters. Okay. The order matters. And here when we're choosing these are both without replacement. Not putting them back. Okay, so permutations, the order is important. And that can be a little tricky if you have a counting problem. Okay. Ask you how many ways you can do something, you will have to stop and think for a minute if the order makes a difference. That's part of the reason why we're not getting too deep into combinations and permutations, because that can be a little tricky deciding if order matters or not when you're first starting out. Let's look at a couple of situations and see if we should use combinations where order doesn't matter or permutations where order does matter. Okay. That's what we're thinking about here. So our first scenario is how many ways can first, second, and third place prizes be handed out to science fair winners if there are 30 students participating. So we've got 30 students and we're trying to pick first, second, and third place prizes. I wonder how many ways we can do that. So would that be, what do you think? Do you think the order would matter there? Does winning first place mean the same thing as winning third place? No, there's like a ranking there, so that there is a difference, probably different prizes even. So order would matter on this one, so we would use permutations. So order matters. Let's look at our second one. Okay, whoa, sorry. All right, this one says if each department needs 2 student representatives from each major on a campus committee, how many ways can the biology department choose the representatives from the 45 students who are majoring in biology? So they're going to pick 2 students out of 45. Does it matter which order they choose them? No, it doesn't make a difference, right? The first person's going to be on the committee, the second person's going to be on the committee, so it doesn't really matter which order they choose them in. So on this one, we would use combinations. Okay. Order's not important there. Okay. All right. Okay, so let's look at the formulas. Let's look at the formulas. So if we want to figure out combinations, okay, then so the idea here, we're trying to choose n objects out of, no, we're selecting r objects out of n possibilities. Okay. The way it's written down. So r, the ones we're choosing, and n, here's the total. If you get them backwards, we'll mess it up. Okay, so r is the number of objects we're choosing, n's the total number of objects we have to choose from. Then we have some notation for this. It's not going to be really important for us. Okay. Here's our little formula. It uses factorial. Okay. Uses factorial. So the total number of objects factorial goes on the top. Okay. And then we divide by the number we're choosing factorial times the total minus the number we're choosing factorial. It's not hard. It looks complicated, but it's not hard. As long as you have the formula. Right? And that's something that will definitely be on the formula sheet. Okay. If we're doing permutations where order does matter, okay, our formula is similar, but it's a little bit different. Okay. So here's the same thing. R is the ones we're choosing, n is the total. So if order does matter, we've just got n factorial on the top, and then just n minus r factorial on the bottom. Okay. So permutations doesn't have the other r factorial. Okay. So let's do a couple. Okay, let's do a couple. So you can see how they work out. They're not as bad as they look. It's just the factorial maybe is a little bit new looking. Okay. Well, let's look. So this example reference is something the book must talk about. I'm talking about a sandwich. Okay. And it says, suppose there are 18 toppings to choose from. Once we've picked the bread, meat, and cheese, how many different possible sandwiches are there if you choose 4 toppings? So here the thing we care about is there's 18 possible toppings for a sandwich. We're going to choose 4. We want to know how many different sandwiches we can make. So the main thing we have to think about, we've got the 2 formulas. Okay? The main thing we have to think about is, does order matter? So we're thinking about, like, does it matter if you put mustard on first and then mayonnaise? Okay, do you personally, you might have some kind of like preference when you're making a sandwich. But as far as what type of sandwich it is, and it doesn't matter what order you put the toppings on. So your order's not important. Okay? So we're going to use combinations. Use combinations. In our combinations formula, so if we're doing n, choose r. How you read that. Then it's n factorial over r factorial times the n minus r factorial. So here n, our total, got 18 toppings to choose from. And then 4 is our r, that's how many we're choosing. at a time. We just plug in and simplify. So on top, we've got 18 factorial. On the bottom, we have 4 factorial. And then 18 minus 4 factorial. Which would be 14 factorial. Okay. So if you see cancellations that can happen here, the 18 factorial and the 14 factorial, everything 14 or smaller is going to cancel out of that. So on the top, we'll just have 18, 17, 16, and 15 left. And on the bottom, we'll just have 4 times 3 times 2 times 1. And that part we can just punch in the calculator, right? So let's see. 18 times 17 times 16 times 15 divided by 4 times 3 times 2 times 1. So here I get 3,060 different sandwiches. So how many ways can we choose 4 toppings out of 18 possibilities? A lot more than you would think, 3,060 different ways. Are you okay with the, I didn't write it down because I was running the room. You okay with the cancellation here? This one's going to be 14, 13, 12, 11, 10. So I just canceled that out with the 14, 13, 12, 11, 10 on down out of the 18. Just left these, the top 4 terms. Okay with that? All right. So get another one. Here we go. Oh yeah, we're good. Here we go. Look at another one here. Okay. Think about this one. It says, consider a race with 140 participants. How many possible outcomes are there for the top 3 positions, gold, silver, and bronze? On this one, we have to think about order. Does that matter? Winning the gold medal is not the same thing as winning the bronze medal. So order will matter here. So we're going to use permutations. Our permutations formula is n factorial over n minus r factorial. So we're picking from 140 people. And we've got 3 that we're choosing. Okay, so for our formula, we'll have 140 factorial, huge number, divided by 140 minus 3 factorial. We can simplify that. That's 140 factorial over 137 factorial. And the thing that happens with the cancellation happens here. So in the top, all the terms 137 or smaller are going to cancel. So that's just going to leave us with 140 times 139 times 138. Okay. So we punch that. Let's see, we're supposed to get 2,685,480 different possibilities. We've got 140 runners, and we're randomly picking the top 3 spots. A bunch of different ways that can happen. Right, one more. Questions on that one? Okay, one more, last one. It says, how many possible ways are there to arrange the order of appearance for the contestants in the local talent show if there are 15 contestants altogether? So will order matter here? Yep, because if you don't want to go first, then think about going first is not the same as going fourth, and you're going eighth. So order does matter here, but maybe you can see how I said that could be a little tricky, but order does matter here. Okay. So we want to do permutations. Okay. The thing that makes this one a little different, we do our formula, is we're picking from a total of 15 contestants. How many contestants are we picking? All of them, right? We're just picking an order, so a little weird, but R is also going to be 15. So what we end up with in our formula, we end up with 15 factorial over 15 minus 15 factorial. That's 15 factorial over 0 factorial. Remember, 0 factorial is just 1. So we really just have 15 factorial. And that's a huge number my calculator won't give me, so I'll just write it down for you. 1,307,674,368,000 even different possible orders. Is that not mind-blowing? He's got 15 people. How many different orders can you put them in? Over 1 trillion? All right. That's it. Last one. Okay, last one. Yeah, that's it. Okay, so Friday be Hawks Day. And come get Hawks help. Come work together with us on Hawks if you want to. If not, I'll see you Monday. Okay. If you didn't get on the sign-in sheet, make sure you get on there before you go. See, I don't see it. There it is. There it is.